We're going over moments and forces at angles in this physics question. Part 1, we're working out density. For Part 2, we're resolving forces to work out the tension in cable C. And Part 3 is an explanation question on this. For Part 4, we're calculating the moment due to the tension force in this cable. And finally, for Part 5, we'll be discussing what we can do to our system to increase the moment. Figure 3 shows a garden gate with a pulley system designed to close the gate. The pulley system raises weight A when the gate is opened. When the gate is released, A then falls. The horizontal cable C passes over pulley R. The tension in cable C causes the gate to close. Weight A is a solid cylinder with the following properties. We have diameter, length, and weight. And then we're given the density of 3 different materials. And for 3.1, we're trying to deduce which of the 3 materials is used for A. So what we can do is we can, with the dimensions that we're given over here, we can work out the density of the material and then compare them to what we have in this table. So I'll start off by just writing these quantities on the next page. So our equation for density is mass over volume. Density is equal to mass over volume. The mass of our object we can work out from the weight divided by the acceleration due to gravity. So 35 divided by 9.81. Which is 3.5678 kilograms. And the volume we can work out by considering that the shape that we have here is a cylinder. So then the volume of that cylinder will be cross-sectional area times length. The cross-sectional area is pi r squared. And the radius is equal to diameter, which is what we're given in the question, divided by 2. So diameter divided by 2 squared multiplied by length. We put these things in, so we put in our diameter, we put in our length, and we end up with 4.162 times 10 to the minus 4 meters cubed. Put all of those things into our density equation, so 3.5678 all over 4.162 times 10 to the minus 4, and that gives 8572 kilograms per meter cubed. And that's the closest to brass. Okay, so for 3.2, figure 4 shows the pulley arrangement when the gate is closed. Pulleys P and M are frictionless, so that the tension in the rope attached to A is equal to the weight of A. A weighs 35 newtons, and the weight of the movable pulley M is negligible. Calculate the tension in the horizontal cable C when the gate is closed. Okay, so we know that the weight of A is 35 newtons, and the tension in the rope that is attached to A is also 35 newtons. We're trying to work out the tension force in cable C, so we can do that by considering pulley M, by considering the forces on pulley M. We're ignoring the weight of pulley M. We're considering the tension force towards the left, which is what we're trying to work out, and then 2 other forces, the tension in these 2 parts of the cable. And they will both be 35 newtons as well. The tension throughout the cable, we're told in the question, is 35 newtons. So then to work out tension T in cable C, we can consider all of the horizontal forces and set them equal to each other. So in other words, forces towards the left equals forces to the right. The forces towards the right would be the horizontal components of the 35 Newton forces. So to work out that horizontal component, what we can do is, we can use SOHCAHTOA. If I draw a line down like this. So for our right angle triangle, our hypotenuse is 35, and our angle here is 55 degrees. We're trying to work out the adjacent length here. So that will be, using SOHCAHTOA, 35 cos 55. And there are 2 of those components towards the right because there are 2 forces. There's 2 tension forces. Each of these tension forces has a component of 35 cos 55 towards the right. So the total force towards the right will then be 35 cos 55 multiplied by 2, and that will equal to our tension. this will be 40.15, or to 2SF, 40 newtons. For part 3, pulley M is pulled to the left as the gate is opened. Explain why this increases the tension in horizontal cable C. Okay, so pulley M is pulled to the left. Right, so we open the gate. This pulley gets pulled towards the left. So as you can imagine, if that were to occur, these strings will become more horizontal as pulley M gets pulled towards the left. That will decrease this angle here. Now the force that we have, the 35 Newton force, that has to stay the same. The weight of A is unchanged, so the tension in the rope, which cancels out the downwards weight force to keep A in equilibrium, that tension force must remain the same. That tension force is the same all along the string, so these two 35 Newton forces are the same. But the angle to the horizontal has decreased as the string becomes more horizontal. If you decrease the angle to the horizontal, the component of this force towards the right will increase. If you have a greater component of force towards the right for these two forces, the tension force towards the left must increase to cancel them out. .4. Figure 5 shows a plan view with the gate open. The horizontal cable C passes over pulley R and is attached to the door at D. The angle between the door and the horizontal cable is 12 degrees. The horizontal distance between the hinge and D is 0.95, and the tension in the horizontal cable is now 41 newtons. We want to calculate the moment of the tension about the hinge. So there's two ways in which we can do this. One way is to consider the line of action of the force, which is this line here. Find the perpendicular distance from that line of action of force to the pivot, to the hinge, which will be this line here, such that this is 90 degrees. That will be the perpendicular distance from the line of action of the force to the pivot. Once we have that distance, we can then multiply that by force, the 41 newtons, to then get the moment of that force. Another way that we can do this is to resolve the force perpendicular to the door. So this line is perpendicular to the door. Resolve the tension force in that direction and multiply that by the distance that we have from the hinge to point D. Either method is fine. I'm going to use the second method. So here is our tension force. That's 41 newtons. If I draw a line like this, then we're trying to work out this component of that tension force here. This is 90 degrees here, and if we were to do, as this would be 12 degrees, 90 minus 12, we can then work out this angle to be 78. We don't have to work out that angle, but it might make things a bit easier. We can then consider that triangle. We know our hypotenuse is 41 newtons, that's this length here. We want to work out the adjacent to the 78, which is the perpendicular component of force to the door. That will be 41 cos 78, and then we can multiply that by the distance of 0.95 to get our answer. And that would give us 8.098 Newton meters to 2SF 8.1. And finally, for 3.5, the same system is attached to an identical gate with stiffer hinges. Now the system does not supply a sufficiently large moment to close the gate. Discuss two independent changes to the design to increase the moment about the hinges due to horizontal cable C. Okay, so we're trying to increase the moment of this tension force. And to increase the moment, we can do one of three things. So I'll discuss them theoretically first, and then we can talk about how we can achieve this practically. The first thing that we can do to increase our moment is simply to increase our force. The second thing that we can do is increase this angle. If we increase this angle, we increase the component of this force perpendicular to the door, which increases our moment. Or the third thing that we can do is increase this distance. And again, that increases our moment. Okay, so to increase our tension force, the easiest way that we can do that is to increase the mass that we have used here. So A's weight was 35 newtons. If it weighed more than 35 newtons, we will have a greater tension force in the rope and therefore a greater tension force in the cable. To increase this angle here of 12 degrees, we can get pulley R and pull it further away from the gate. The further this is from the gate, the bigger this angle would be, the bigger the component of the tension force perpendicular to the door, and the bigger the moment. Now increasing the distance of D from the hinge, so in other words increasing this distance here, has two effects. So one, obviously this distance is bigger, so in our calculation when we times by 0.95, that will increase our moment. But if we're to pull point D further away from the hinge, we'll also decrease this angle here. And if we decrease this angle here, then we will be decreasing the component of the force perpendicular to the door. So increasing that distance increases this quantity, but decreases this quantity. So we can't quite tell exactly what that would do for our moment. So I think the safer answers would be to increase the mass, therefore increasing the tension in this cable, or to pull the pulley further away from the door to increase the angle and therefore increase the component of tension perpendicular to the door.